What we're going to be looking at here is something known as the vector cross product. Now, this is a little bit weird, but if you remember back when you were first learning math and you're learning multiplication, they said like 3 times 2 equals 6, and you used this x in order to say multiplication. And then later on, you learned that 3 times 2 equals 6, where you were using a dot. And then later on, you just said put everything in parentheses because our paranoia has finally set in, and this also means multiplication. Well, this dot we have already used previously in the year when we discussed work. It was called the dot product. If you recall, work was equal to a force dotted with some displacement. And that meant that we had to look for the force vector that was going in the same direction as the displacement here. This resulted in our equation reading as FD cosine of theta. Now, if that's the dot product, what this is actually up here is what we're going to be talking about today. This is the vector cross product. We use this vector cross product a number of times in the world of physics, but we're going to start using it in this unit when we talk about torques. Now, the vector cross product is a little different than anything you've previously done because the vector cross product is looking at very specific components of the forces. So what we're going to be doing here is we're going to be looking at how if I have 2 vectors, how I can take the components of the vectors and multiply them together. So notice here how there's 2 vector components. There's one that's parallel, that's the dot product, and then there's this one that's perpendicular, okay? This one here, that's the one we want. We want that perpendicular component to the vector, and that means that if we take a look at the angle that separates these as theta, this is our opposite side. So we're going to be looking at sine components here whenever we use our cross products to find the component that is perpendicular to the vectors. And we'll be talking about that a lot more when we start discussing torques. Now, one of the things I'm going to show you right here is a cross product example if you're using matrices or a 3x3 kind of 3-dimensional world. And we're going to be doing this with unit vector notation. So this is like I hats, j hats, and k hats, and then I, j's, and k's. You might not need to use this in my class if you're in the CP Physics. The AP Physics may be using this on some of the tests, but if you plan on going into an engineering or a science major in college, you'll definitely see this stuff, especially at the high level calculus. So we're just going to take a look at this because it's not difficult, and we're going to solve this cross product using a 3x3 matrix. Now, what we're going to do here is we are saying that vector A crossed with vector B is going to equal another vector. It's going to equal another vector C, and this vector C is going to be orthogonal or perpendicular to both other vectors, which means that this new vector C has to exist in a 3rd dimension. You'll oftentimes see physicists making this symbol with their fingers. That's because if we think about an x and a y-axis, the only way I can create a new vector that's perpendicular to both of them is to go in a new 3rd dimension. This z-axis here is perpendicular to the y, and it's perpendicular to the x-axis. So this orthogonality, or perpendicular to all other vectors, is what we need to have here. And the way we do this is with a determinant. And this is a matrix term. That's a mathematics word from linear algebra. But it's a very simple and straightforward thing to do. What we're going to do, though, in order to solve this with our vectors A and B up here, is we're going to make a very large matrix here. Okay? And the first thing we're going to put in this matrix are the letters I for the x direction, J for the y direction, and K. This is like I hat, J hat, K hat for directional vectors. Then what we're going to do is we are going to put in all of the I, J, and K components of vector A. So in the I direction, that coefficient is 2. In the J direction, it is 3. And in the K direction, it's negative, don't forget that negative sign, 4. We then do the same thing, but for the B vector. this is going to be 5, negative 6, and then a positive 7. Okay? If we take the determinant, often written as just det, of this 3 by 3 vector, it's a 3 by 3 because we go 3 across, I, j, and k, and then 3 down, the vector, and then 2, 5, and then 3, negative 6, negative 4, negative 7. This will equal our third resultant vector c here, this orthogonal component. Now, the way we do this is a little strange. We actually take a 3 by 3 determinant by breaking it up into a series of 2 by 2s. And what we essentially want for our final answer is we want something that's going to read some number in the I direction plus some number in the j direction plus some number in the k direction. Some amount of x, some amount of y, and some amount of z. Now the way we do this is in order to find what is going on in the I direction, we need to look at the other two directions to solve that. And the way we do this is we look at j and k, our other two directions, and we go left diagonal, then right diagonal. So we look at these values first, and then we look at these values second. And the way this looks whenever we write it out is that we'll take these first two values, 3 times 7, and multiply them together first. So it's going to be 3 times 7 minus, and then the negative 6 times negative 4. This is what is going on in the I direction. So if we did that, 3 times 7 is 21. Negative 6 times negative 4 is positive 24. 21 minus 24 is negative 3 in the I direction, or the I hat direction. Now, when we write out these determinants, a common way of doing this is to recognize that our I value is going to be positive, and then we're going to do the same thing here in the j direction, but due to the fact and the nature of the way determinants work, we're going to throw a negative in front of the j. So we're going to do a very similar thing here, except we're going to start with just a random, it almost seems random, a random negative that gets thrown out in front, and then we're going to do this for the j direction. Now for the j direction, for this to work, we need to look at the other two vector directions, I and k. So we're going to come across with 2 and 7 first, and then we're going to come across with the negative 4 and the 5. So we're going to get a negative, and then we need to multiply together the 2 times 7. I'm going to put this in a big bracket, and then subtract that from the 4 times, I think this is a negative 5. Oh no, it's a negative 4, excuse me. Negative 4 times 5. And this is what's happening in the j or the j hat direction. So 2 times 7 is 14. 4 times 5 is 20. It's negative 20 because the negative 4. The negative of a negative makes this positive. So we've got, we'll just write this down real quick, 14 plus 20, so that's 34. But then there's this negative out in front. So in the j direction, it's negative 34 in the j hat or the j direction. Now, when we do the k direction, we go back, we now have a positive in front again. So if we think about the values that go in front, positive, negative, positive, the way that works, we're going to have a positive, and now we need to do the exact same thing again, but in our last two vector directions. We've already done j and k, we've done I and k, now we need to do I and j. So 2 times negative 6 followed by 3 times 5. So when we write this out, we're doing the quantity of 2 times negative 6 minus, and then on the right hand side, that's going to be our 3 times 5. And this gives us a quantity in the k direction. 2 times negative 6 is negative 12 minus 15. So that's going to be negative 27. So we've got negative 3i minus 34, and now we have minus 27 in the k direction. And this is actually what vector c will equal. So it's a little strange looking at it and doing it, but that's how you do it for a 3 by 3 determinant here. Okay? So we have all of those bits and pieces that are going on there in this way. So it's kind of a strange thing to look at, but it's nothing too crazy. Another way to do this is to find the parallelogram. Parallelogram that is generated between these two vectors for a cross product. So if this was vector A and this was some vector B, we'll make these vectors. I want to figure out what the area of this parallelogram is. So it's an area of the parallelogram. Now, maybe you're looking at this parallelogram and you're like, wait a second, this looks like a rectangle that was just shifted a little bit, right? Like it looks like this triangle that exists right here, if I could just put it back over here, I'd be golden, right? Because then I would just have, I'd have a shape that was just like a big rectangle, right? And a rectangle is just like a length and a width. So if I could figure out, whoops, how did I get rid of that? If I could figure out a way to get rid of just this little edge here, then I could figure out what the area of this parallelogram is. And in reality, what that means is I just need to find what this height is right here in green. If I can figure out what this is, then I'm finished, because that will give me just a length and a width. So to do this, what we can recognize is, given that there's some angle between these two vectors, I am just looking for the vertical component of the B vector. And if this is vector B, this is the opposite side of it. This means to find it, that opposite side is just equal to B times the sine of theta. Remember, sine of theta is the opposite over the hypotenuse, and B was the hypotenuse here. So when I brought it up into the numerator, the opposite side is just B sine of theta. So this would be like the length of this parallelogram, or this rectangle I'm trying to create. So that means that if I wanted to get that area, I could just say it's, well, A times B sine of the angle between them. And that's it. So we can quickly get that cross product and figure out what that new vector is, that vector C, just by saying that it's equal to AB times the sine of theta. And this is what we were talking about briefly in the very beginning here when I was pointing out the sine of theta term here for the vector cross product. And this is what we're looking at. We're looking at this opposite side to figure out how much is perpendicular to that, which we'll see in torques. One other thing we could look at here for a cross product, this gives us the magnitude of the cross product here for C. It tells us the size of it, but it doesn't tell us the direction. In order to do that, we have to use something known as the right-hand rule to show the direction of this vector. And the way I like to do the right-hand rule, and it's a little weird, is when I look at two vectors like A and B right here. Here's vector A, and here is vector B. I like to take, if I'm taking A cross B, I like to take my fingers, and I like to align my fingers. That's your 4 fingers, not your thumb, your 4 fingers. I like to take my 4 fingers and align them in the direction of that vector. What I'll then do is I will then curl my fingers through the smallest angle possible to strike the other vector. So that's this angle right here. I'm not going all the way around because that's a giant angle. I'm just making the smallest angle possible. When you do that with your fingers, when you curl them, and you'll actually hear sometimes that the cross product is known as the curl, but when you curl your fingers like this, your thumb will point in a direction. And this direction of your thumb, this thumb is the resultant C vector. It is that vector that is orthogonal to the other two. And if we look at this picture right here, we easily see that this vector C is perpendicular to both A and C, and this is the thumb right here. Okay? That thumb tells you the direction of this last vector. So if you have a 3x3 matrix, this will tell you the direction because you have x, y, and z, the I, j, and k. But if you don't have that, if you just have two vectors and you're doing AB sine of theta, then use your right-hand rule in order to find the direction that this new orthogonal vector C is going. If you use your left hand, I'm going to have to chop off your left hand. Okay, so only use your right hand here. It's the right-hand rule. If you are doing anything with torques or you're doing anything with magnetic fields later on in the AP2 class, this right-hand rule is huge for you to do and understand the world of physics. Okay, so this is just a quick little tutorial onto some cross-product stuff and matrices. We don't need to really concern ourselves a whole lot with it in the CP class, but it's more just showing that to you and making sure that you have everything you need to be successful later on. So I hope you enjoyed this video. If you got questions, hit me up. Let me know what you need. Until then, check out the next video on torques where we'll see some more of this cross product and it'll make some more sense. And have a good one. Adios.